9.5 Lesson 3 Alternating Series. The objectives for today's lesson are: you'll know the relationship between a series and its corresponding absolute value series. So we'll start the lesson today by having you do work on a problem that will help you to understand this relationship between a series and its corresponding absolute value series. And then that will lead us to Theorem 9.16 about absolute convergence. We will learn vocabulary today. What is the definition of an absolutely convergent series? And what is the definition of a conditionally convergent series? So vocabulary for today are absolutely convergent and conditionally convergent. Right now, we will take a look at a problem that will help us with Objective 1, so that you will understand the relationship between a series and its corresponding absolute value series. And this problem will also help us to understand Theorem 9.16 about absolute convergence, and it will also help us to understand the definition of an absolutely convergent series. This is the series that we're looking at. You should write the first 6 terms of this series. So these are the first 6 terms of the series, and what I'd like to emphasize is that this is not an alternating series, because we do not have alternating signs for consecutive terms. So the first term is positive, but the second term is not negative. We have positive, 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 and then a negative term, a negative term, and a negative term. So this is not an alternating series. When we're considering a series in this chapter, the question that we have about the series is, does the series converge or does it diverge? So what have we learned so far about determining the convergence or divergence of series? We have the definition of convergent series. You look at the sequence of partial sums, and if the sequence of partial sums converges, then we say the series converges. And we use that definition when we're looking at telescoping series, because we can easily write a formula for the nth partial sum and see if the limit of s sub n as n approaches infinity exists. And if it does, we would say that our telescoping series converges by definition. But this does not appear to be a telescoping series. We've also learned about geometric series, but this does not appear to be a geometric series either. We've learned about something called the nth term test for divergence. It states that if the limit of the nth term as n goes to infinity is not equal to 0, then the series diverges. But we can't use that here because the limit of the nth term as n goes to infinity is equal to 0, so we can reach no conclusion using the nth term test for divergence. We cannot use the integral test because we don't have the corresponding real valued function f of x is equal to sine x over x squared. It's not positive. It would be continuous, but it's not positive, and it's not consistently decreasing. So the integral test is out of the question here. We don't have a p-series here, so we can't use that either. The direct comparison and the limit comparison tests apply to series with positive terms. We have a series that also has negative terms, so we cannot use those tests either. And as we saw, this is not an alternating series, so we cannot use the alternating series test either. So the question is, how can we determine if this particular series converges or diverges? So here we have the series that we were just considering, and look at the one that I'm writing underneath that. All I'm doing is I'm considering the series whose terms are absolute values of the terms from our first series. So we call this the corresponding absolute value series because it has the same rule as the one that we began with, but we're considering absolute values of the terms from our first series. So we call this the corresponding absolute value series. Now, because the corresponding absolute value series has terms that are positive, we can use the direct comparison test. So now we would like to use the direct comparison test, so we need to choose a comparison series and do a term-by-term comparison with the terms of the series that we have here, and then come to a conclusion about convergence or divergence. So it turns out that this particular series converges, and we can show that this absolute value series converges by comparing it to a P series. Now we will do a term-by-term comparison. If we can show that this relationship is true, that the nth term of our absolute value series will be less than or equal to the nth term of the comparison series, then since the comparison series converges, our series, which would have smaller terms, must also converge by direct comparison to the convergent P series. But how do we demonstrate that this relationship here in the inequality is in fact true? One thing that you can note is that in the denominator we have n squared for both nth terms, and it doesn't matter that you have the absolute value of n squared. N squared is positive to begin with. So they have the same denominators. So the nth term with the smaller numerator will be smaller. So how can we argue that the numerator of our absolute value series will be smaller than 1? You go back to the range of the sine function, which is between -1 and +1. Therefore, the absolute value of sine n has to be less than or equal to 1, showing that the numerator of our absolute value series will always be less than or equal to 1, and thus proving the inequality that we have here. So we can state by direct comparison to this convergent P series that this absolute value series must converge. That allows us to state the conclusion that the corresponding absolute value series converges by direct comparison to the convergent P series. But now we have to think, what does that tell us about the original series? We're going to take a look at a theorem that will answer that question. Theorem 9.16 about absolute convergence. So now we take a look at Theorem 9.16. What does it state? It states that if the corresponding absolute value series converges, then the original sine series also converges. Before we take a look at the proof of the theorem, let's just go ahead and use it for the problem that we were working on. So by Theorem 9.16, we can conclude the following. The hypothesis of the theorem states if the corresponding absolute value series converges, and we saw that with our example, we saw that the corresponding absolute value series converges by direct comparison to the convergent P series, this theorem allows us to conclude that the original sine series also converges. So we're able to reach the conclusion that the original sine series converges by using this theorem. Before we take a look at the proof of Theorem 9.16, let's look at vocabulary. This series here is called absolutely convergent. Why? Because its corresponding absolute value series converges. So this series here is called absolutely convergent because its corresponding absolute value series converges. And this is the definition of absolute convergence. A series is absolutely convergent if its corresponding absolute value series converges. Now we take a look at the second definition. You could have a series that is conditionally convergent if the sine series converges, but the corresponding absolute value series diverges. And we're going to look at a very simple example for that. Consider this alternating series. We can quickly show that this alternating series converges by the alternating series test. So we check the limit of a sub n as n goes to infinity, and it is equal to 0. And we check to see that a sub n plus 1 is less than or equal to a sub n for all n greater than or equal to 1, where n is an integer. So is that true? It is, because you can show that 1 over n plus 1 will be less than or equal to 1 over n for all n greater than or equal to 1, where n is an integer, because these are two fractions with the same numerator, so the fraction with the larger denominator will be smaller. So we do have a series here that we know converges by the alternating series test. So now let's look at the corresponding absolute value series for this alternating series. So here we have the corresponding absolute value series for our alternating series. And notice that n starts at 1 and n is an integer. So 1 over n will be positive for any n starting at n is equal to 1. So we don't really need the absolute value for the 1 over n, because it will be positive. So what the absolute value will do is get rid of this particular part, which is giving us either positive terms or negative terms. The absolute value will make all of our terms positive, so we can simplify what we have for the corresponding absolute value series just by writing this. And we recognize this to be a p-series with p is equal to 1, so this is the harmonic series and it diverges. So we have here an example of a series, and the series that I'm referring to is the one that we started with. And this is what we call a conditionally convergent series, because the series that is signed converges, but the corresponding absolute value series diverges. So we looked at an example to help us with objective 1, so that we looked at the relationship between a series and its corresponding absolute value series. And then using that example, we looked at Theorem 9.16 about absolute convergence. Theorem 9.16 states that if the corresponding absolute value series converges, then the original signed series must also converge. And then we use that to look at the definition of an absolutely convergent series. The example we began our lesson with was absolutely convergent because its corresponding absolute value series converges. And then we also looked at an example for the definition of a conditionally convergent series. What we're going to do now is we're going to look at examples 5 and 6 from our textbook, so that we have additional examples to work with for these definitions and the theorem. And then we will conclude by looking at the proof of Theorem 9.16.